Okay, so welcome back to another video. Today is going to be a very interesting problem we want to evaluate. We have e divided by the square root of e multiplied with third root of e divided by the fourth root of e times the fifth root of e divided by the sixth root of e. And we see the pattern, there's a 7th root, 8th root, then 9th root, 10th root, so on and so forth. So it's an infinite products dealing with the nested radicals of as you raise the index by each one. So this one's actually not as bad as you think just from the confusion. The main thing is to figure out like what is the symbolic notation on how to write this infinite sum. Then from there we can actually just do a bunch of, rewriting and actually applying the natural log series, including since we have the base e there. So not a lot to it, but I think this is actually one of those cool problems. I think it's worth, checking out just more on the fun side. So with that, let's actually just jump right in. So if you analyze this entire infinite product series, well, this entire thing of the expression we want to find, you play around with the numbers and try to figure out a pattern what works such that we actually get this, expansion. What it comes down to is that we have this is the infinite sum starting at n is equal to 0 of e to the power 1 divided by 2n plus 1 and n divided by e to the power 1 divided by 2n plus 2. So with that being the case, we can actually notice that they share the same base and that we can actually put this under just one base of e. So now I'll write this as now the infinite sum n is equal 0 of e to the power 1 divided by 2n plus 1 and then subtract 1 divided by 2n plus 2. And don't forget, I should also call this p for, the expression we're trying to, calculate. So with this being the case, how will we actually tackle such, infinite series, or the infinite product series? I should have said it like that. In a situation like this, let's actually suppose that this does converge to some value. With that being the case, we can let's now actually take the natural log of both sides, as I mentioned earlier. So we have that ln of p is equal to ln of this infinite product series over here. So e, then 1 divided by 2n plus 1 minus 1 divided by 2n plus 2. Okay, so with that being in mind, we know that if we take the natural log of the infinite product series, then that actually converts to such that we have the infinite sum of the natural log of what's inside of our, series that we're actually, working around with. So with that being the case, so we can using that continuity, so we have the infinite sum at n is equal 0 of ln of e of this entire thing over here, so 1 divided by 2n plus 1 minus 1 divided by 2n plus 2. Then ln of e just gets rid of itself and then we're just left with the exponent. So now we have the infinite sum over here as n is equal 0 of 1 divided by, so let me actually put this in parentheses since we're actually splitting this up over here, so not to get the confusion such that it's like separate by itself. So 1 divided by 2n plus 1 subtract 1 divided by 2n plus 2. Now let's actually just write out a few numbers just to get an idea like what's this expansion looking like. So if I plug in 0, so I have 1 over here, then I subtract that, so this is 1/2. Then we add this with now plug in 1, so let's see, this is going to be 1 over 3, then subtract 1 over 4. Let's do this a couple more, so that means do this again for n is equal to 2, so 1 over 5 and then minus 1 over 6. So we get the picture, so on and so forth with that. So notice that we have a plus, minus, plus, minus, plus, minus, so that being the case, that's actually an alternating series. And we actually do, yet again, enough inspection to the point that we can actually write this as an entirely different infinite sum. So we have that p, so I should first write the letter p first. So we have that p is equal to, so the infinite sum yet again. This time our index we're going to start with n is equal 1, and then this is alternating, so I can write this like as -1 to the power n plus 1, and then divided by n. So you might be thinking that, how do we actually tackle such sum? Actually, you might be thinking, we've seen a sum like this, right? So you can actually show that indeed that this does converge to a value just by applying the alternating series test, and indeed it does. But and then there's several ways to actually calculate this such that it does converge to that specific value that we're looking for. The easiest way to do this is note that the following expression slash function, the natural log of 1 plus x, it actually is equal to this infinite sum. So let's see, infinity, then n is equal 0, or rather this is supposed to be equal to 1, n is equal to 1. of -1 to the power n plus 1, then times x to the power n, and then divided by n. This being, of course, that the absolute value of x is strictly less than 1, in which indeed it does converges that such that if I let x equals 1, then it actually does work in this situation over here. So let x equals 1. So then therefore ln of 2 is therefore, if I just plug this in, the infinite sum as n is equal 1 of -1 to the power n plus 1. So that's just 1 to the n, so it's just 1, and then divided by n. And then there we have it. This is equal to this, so p is equal to, or rather, ln of p, because what I haven't done is that I actually didn't take the e base, and I actually just gave that last step away. So ln of p is equal to ln of 2, then take the e base to both sides, and we get that p, the expression that we want to compute, aka this entire thing, is indeed does converge to the number 2. And therefore, there is our final answer for this infinite product series that, you know, it actually very looks like eye candy to all the math viewers out there. At least I think so personally, but you know, there we have it. So yeah, that's pretty cool if you ask me.